there is also more because we have extreme quantization now. It's not just 4 bits, it's 1.58, and they call it 1 bit, but it's obviously more than 1, right? Because it's tertiary. They call it ternary and tertiary bits because it's not just 0 and 1. It's, was that -1, 0, and 1? The values apparently
that's the real ternary, yeah.
Ternary, okay, ternary, right? So we have models like Bitnet that are like 158 bits, and they claim also that they're faster on CPU on ARM than Llama CPP. Obviously, always compare yourself to like the incumbent. That's very convenient. Lower memory and computation. They use that in fine tuning. So I'm not like there's a slide where like we really show all that exists, but this is also possible. We can go as low as as 158 or 2 as well, right?
Though there is a caveat to this specifically, is that this is not quantizing an existing model, typically speaking. This I believe this is training a model with this Bitnet technology and then running it at full precision, which happens to be 1.58 bits per weight.
So what do you, when you read the Llama 3 8B 158 100 billion tokens? Yeah. Did they retrain Llama or did they post-train it? What did they do with it in order to call it like a 158 bit?
I imagine it's some post-training, hence the 100B tokens, but that's a fair point that I should look at before I make my claims.
Yeah, because like it's like a fine-tuning technique, maybe. I don't know where to put this. Is it a quantization, or is it a fine-tuning? Is it something that comes on top, or like the usual quantization where like you don't touch the content, the parameters, right? Like you touch the bits, but nothing else. But it seems like these Bitnets frameworks are doing a bit more, touching the weights, like the parameters, the embeddings, the dimensions, stuff like that.
I think this comes like kind of in between. Like after you do the training in the full precision, you get all of the benefits of like the full precision model training. Then you do like something like, it's not like a form of like a QAT, like quantization of your training, where you dedicate a subset of tokens, for example, in this case, 100B, and then you just like do like additional training stage where you simulate quantization during training. And then you have to do some tricks kind of to stabilize it and so on, but then you kind of benefit from all the knowledge you learned during pre-training, and then you end up with like a quantized model in the desired scheme that you impose. And this usually is kind of like in between.
Oh, it's not like a pure quantization. It's quantization
you get the
post-training.
Yeah, I mean, they're like two techniques here, like quantization with training and post-training quantization. Post-training quantization is what we are all like doing here, like all these like Q4 and so on, Q5, and all of the quantization we're doing in LM compressor. But kind of QAT is like more expensive one because you need training infrastructure, you need a training data set, you need to like stabilize the training, tune hyperparameters, and so on. But the benefit is that you will get quantized model at the end of it. You don't need to do PTQ, what we are doing here. And yeah, this is kind of a little bit harder to do. But if you have resources to do that, you should more or less do it always, because you should probably always end up with a like slightly better model than what you will get with PTQ. It's just like you put more compute on top of it, and yeah, if you do it right, it should be a really high quality quantized model.
Interesting. But what do you think is the data set? Like, is it like a big data set, or like just like something to run on top? Is it like distillation or stuff like that, or?
It really depends on what the target is. Like, yeah, like you can do QAT specifically for specific tasks. That's something that we used to do before. For example, you have base pre-trained Llama model, and now you want to fine-tune it on some instruction following data set, which is something you can run on maybe 4-8 GPUs, something very reasonable. And that's a set framework where you can attach QAT on top of that and immediately fine-tune a model on the target task with QAT, and you end up with quantized model fine-tuned for that data set.
Right. So
but
QAT,
doing this.
QAT, like just for the audience, means like a quantization aware training.
Yeah,
Is
that's
that
right.
what that means?
Yes,
Okay, it's
yes,
cool.
that's
Yeah,
right. You basically simulate quantization during training. So during the forward pass, you kind of fake quantize everything so that your weights are kind of doing that. But then during the backward pass, because quantization is not differentiable operation, you kind of do it in the full precision. So you do full precision backward. And then again, you do forward pass with kind of fake quantized weights, and then you update everything back in the full precision. And that's how you go back and forth. Yeah.
That's insane, man. Fake quantization. Fake quantization.
Yeah, because you want to simulate that to a model, so that the all of the activations and the loss are kind of tuned for this quantized setup, so that the outputs are not in full precision, but actually they have some errors from quantization.
Okay, so but in terms of accuracy, like would you lose some accuracy in the forward stage, or?
I mean, it's so in terms of the accuracy versus just doing it like as we are doing it like a PTQ.
As is.
It's either the same or better. So that at least if you do it right, it should never be worse than PTQ.
Okay.
But now, given that we have methods with like these like PTQ tricks, like where we do like very efficient like 4-bit, 8-bit quantizations, where we lose 1 or 2%. It's now a question of whether it makes sense for your deployment actually to do that. Do you really want to put that many resources just to get 1% higher accuracy? So yeah, it really depends.
Gotcha.
But if you do it right, it should not be worse than doing PTQ. Definitely.
Interesting. Okay, so one other question I had for Colin is I think when I was reading about quantization, especially GGUF, I was talking with the maintainer of the Python version of Llama CPP. And so we were discussing, I was reading stuff on Reddit. Obviously, as I said, like what's his name? Ivan Kavrakov. He didn't want to document anything. So at some point, there was a confusion. The documentation, or even Google, would tell you that GGUF, which is a format, came after GGML, right? GGML means Georgy Garganov ML, machine learning, by the way. That's what it means, the acronym. But the tensor library is GGML, as I understand, right? But then like all the documentation is saying GGUF is replacing GGML. And it's a format, it's not a library. And then a lot of confusion was still to this day is present around the naming convention, what those name means, like what is the library and what is the format, right? Can you help a bit differentiate between these two? Like what's the relation? Which one is like truly the format? Which one is still a library only?
Yeah, so this is one of those ones that was also an unfortunate naming convention that was caught early enough to, and even then caused a lot of controversy at the time. But it was caught early enough to kind of correct the path. So initially, models were just saved with the .ggml path, and they were called GGML models because it was using the GGML library. But then partway into it, and or .bin even, like people just like called them whatever they wanted. But then a couple of years ago, I think now, there was a push for a more standardized file format, and this GGUF is a unified format, I believe, is what the UF is.
Yes.
Came into
GPT
creation. Yes, and so what it did was it standardized the way that the models are saved and loaded in very important ways. Like we can see there's a ton of interesting stuff that's come from it, like Hugging Face. Now if you go onto a GGUF page, you can explore the model itself and like the information about it, all of its values, what the layers are quantized to, like that's visible to you in your browser because
the blocks, the super blocks.
Exactly. because gguf is this very standardized format that is now being used to save all of these models. And so it really unlocked going forward a much easier path, especially when it comes to adding stuff. Like there's been times where they need to add extra tensors to represent the rope scaling, for instance, and that's like kind of trying to extend the context of the model. That needed to be saved within the file itself. In ggml, it kind of just would have been put in somewhere and hopefully pulled out something in the right place. But gguf, yeah, it standardized it, it made it maintainable, and it was a very important step taken. That's honestly a lot of the Llama CPP's relatively recent history has been around these painful refactors that are critically important for the health and future of the platform. And that was one of the earliest ones, to my memory at least.
So can I say GGML is a library?
Yes.
Still? Okay.
Yes. And it is still a maintained library.
Say again?
It is still, like, if you go to the it's called the GGML organization now, their GitHub has the tensor library still, and it's used in Llama CPP.
Right. It's still used it's a core library within within
it hasn't gone away.
Llama CPP. Right.
Yeah.
But back in the days, it was GGML library plus format as well.
Exactly. Yeah. So it had that confusion and the crossover that didn't make sense actually, and so they refactored it, much to the dismay of many people. But it now, and in fact, so much to the dismay, there's a fork of Llama CPP called Cobalt CPP. And it is more than just a fork. Like they have added a lot of their own stuff there as well, and it is quite a nice platform for running inference. But they have maintained backwards compatibility, I believe, even all the way back to the GGML, like original files. Like you can still load them up on the. It's caused them crazy headaches. I keep telling them to stop doing it, but they have the backwards compatibility for years. It's crazy what they do over there.
That's sick. I got a question to Eldar though. So because I've been asking this question in the VLLM Slack, to be honest, and I was always wondering, what is stopping the VLLM community for like leveraging something like GGUF? I'm not saying like copy paste or something, but like being inspired by something like that instead of having like a clutter of files from Hugging Face every time you need to load a model with the config, the .json and all that stuff. Like, what is keeping the community, the maintainers, for adopting something like that would just make life easy?
So right now there are two things there. The first one is like, if you want to run GGF models in like VLM, you can actually do it. I think there were like some like community contributions to actually enable.
It's experimental though. It's like
it's still experimental. It's probably not the fastest thing that you would get, but at least you can run it if you really want to. But there was like the same problem that Colin just explained also happened in the quantization world when GPTQ, like that was like the first kind of one of the first algorithms which actually like went viral, was like able to do the int4 quantization for specifically for GPUs, came with like very good kernels to run that on GPUs. It used one format like to save the quantize, because when you're quantizing to int4, you have to pack your weights, right? Because you have like int4 weights. Now you have to pack them into like for example like 16-bit weights or something like that, and then GPTQ used one way of packing this. Then at the same time, there was bits and bytes, and they used different formats for packing. And then I think AWQ came with completely different now format for packing, and they all had like different formats to save the quantized models. And then when you're actually writing an inference kernel for 4-bit model, you now have to consider all these different versions of like quantized models, because now you have to know how did they pack so that you can unpack as very, very efficiently. And that all like caused a ton of confusion, because sometimes you take GPTQ model, you would load it up, you would run it, you would get like garbage outputs from a model just because the unpacking wasn't done in the way that the packing was performed on the GPTQ side. And actually, we created the kind of like a standard for this called compressed tensors. This is now like a standard which Hugging Face also adopted as part of the transformers, which actually specifically like sets the standard on how to save quantized weights on a disk. And now it's also been adopted by VLLM, and now that's what, for example, also LLM compressor is using. So now whichever format we use for quantization, FP18 to 18 weights, activations, blah, 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 there will be a unified format to save it. It will be compressed tensors representation. And then VLM will know, or Hugging Face transformers, they will know exactly how to load the model, which bits represent like assigned bits, which represent weights, and so on and so forth. So yeah, there was also a lot of confusion there, and I guess we are kind of trying to get around that with the compressed tensors.
Yeah. It's about time, man. It's about time because you're gonna have a lot of users and adopters, so it's time to converge to something really global, universal.
It was really frustrating period, especially for academics, because when you want to reproduce like results from a paper, you just want to run it as quickly as possible just to get some numbers and move on back to your projects. But then you get garbage output, and then you start wandering around what's happening, and then you spend 2 days just like trying to get the proper replication of that.
Woo.
Yeah, it was a huge headache. Yeah.
So LM compressor. So go ahead.
I want to say one thing. First of all, safe tensors. Very happy that format exists. That's a nice standardized format. Again, similar thing where you can load it up in like the Hugging Face view and see everything about the models. And I feel like there's this idea of why do you have config.json, tokenizer.json, tokenizer config.json? Why don't you just have one single file that users load up? And my counterpoint to that is actually like look at the commit history of what you're showing right now. Add extra tokens, update config.json, things like that. Like you can't do that in GGUF. I love GGUF. It's great. The models that they create are great. But editing it after the fact, after it's made, it actually becomes, for me, in a lot of cases, more efficient for me to just delete the model and redo it. Because my automation script is like, it's nice and set up. Like I can just click one button and it goes. But if I need to update the chat, the chat formatting, the chat template, I have to download the model, run a script, and then re-upload the model. Like it's a hassle. Like every single quantized version, if I upload 15 of them, I have to download each of the 15, run the Llama CPP script that takes out the old one, puts in the new one, and then re-upload that whole file. So there is a give and take. Like, yes, it is simple, especially for an end user. I love the experience for an end user to say, here's my one file, load it up. But in terms of like development and trying to be, especially like the enterprise side of things, I can imagine as well, like being able to discreetly change individual parts, edit your tokenizer config.json manually, and just upload that one line file change. Like that's hugely beneficial from a model maintainer perspective. So there's definitely a give and take.
Yeah, I totally get it, because from the end user standpoint, we like having like one model to load, and especially if we could even quantize a model. So like I'd rather quantize a file than quantize a bunch of files. Maybe I would lose one or forget, or I'll make mistakes and stuff. But if it's one file, I'm sure everything is in there. So if I do inference or quantize, I have everything I want. I wonder if like there is no like a middle ground between these two. I know that LM compressor has like a recipe, so you just tell it everything. Maybe chat template as well. I don't know, Elder, you can confirm. But in the meantime, like even for GGUF, you can do that in a CI/CD pipeline, and so like you can deploy every time there's like a meaningful patch. And like when you modify a small thing, if it's like worthy of a new deployment, fine, and then like you just run the pipeline and you will have like a new patch, or there's a specific changes that would warrant that kind of update of the GGUF, instead of like creating a new one for every small change, because people are not going to die. The earlier version is also good. It's just that like you're improving it, along the way.
Right. What I mean more so is like when I have if I create a repo for a model and then I find out that the chat template is wrong, I'm just going to run my script a second time from scratch and upload it to the same repo to just replace all the files in place, because that's easier for me than manually going and downloading each individual file, editing it, re-uploading it. Like it's such a hassle to have to, like, it's basically a black box. Like, while there's a lot of visibility into it, editing it is not easy. So that's where the trade-off comes from.
Got you. Obviously, we have Olama, we have VLLM, we have local AI, we have LM Studio. I guess like you've been working with. Can you tell us what you've been doing for LM Studio lately in terms of quantization?
Yeah, the main thing is, like, if you go to the LM Studio community on Hugging Face, the GGUF models are the ones that I had been creating and uploading. They've also got MLX going on now from someone else, so they're just kind of maintaining a library for LM Studio for the users to have, you know, a list of basically these are high quality known working models. You can download anything you want, but if you download from here, you're going to have a good time.
Nice. And I know that Olama, for example, you can download directly from Hugging Face. Is it the case for LM Studio as well? It's like you can like just put the like a Docker image kind of name in, and then it will just load it for you.
Yeah, so they have like the CLI similar to Olama, where like you can say I don't remember exactly. LMS, like LMS pull and then the model name. But then also the LM Studio is designed more around the graphical interface.
Yeah.
So you would go to the model download, and you can find anything from Hugging Face there.
Interesting.